Welcome to this problem walkthrough. Today, we'll explore a fascinating challenge, finding the maximum font size that allows a sentence to fit within a given screen. This problem is known as problem number 1618, maximum font to fit a sentence in a screen. We'll break down the approaches and concepts step by step to help you master this task. Let's dive in. In this problem, you are given a screen with fixed width and height, and a sentence that you need to display on the screen. The objective is to find the maximum font size from a given list of font sizes that allows the entire sentence to fit within the screen dimensions. To determine if a font size is valid, we use a provided font info interface. This interface includes three key methods: getWidth, which gives the width of a specific character at a given font size; getHeight, which provides the height of the font at that size; and canFit, which directly checks if the font size is valid. For a sentence to fit, the total width of all its characters must not exceed the screen width, and the height of the font must not exceed the screen height. Your task is to implement the function maxFont, which calculates the largest font size that meets these criteria. The input to the function includes the sentence to be displayed, represented as the string text, along with the screen's dimensions, W4 width and H4 height. You are also given a list, fonts, which contains all possible font sizes, and the font info interface for querying font dimensions. The function should return the maximum font size that allows the sentence to fit within the screen. If none of the font sizes work, it should return -1. For example, consider the input where the sentence is LeetCode, the screen width is 100, the height is 20, and the possible font sizes are 10, 15, 20, 25. Using the Font Info API, we will determine which font sizes allow the sentence to fit the screen and find the largest one among them. For this example, the output is 15. Here's why: font size 10 results in a total width for the sentence that is too small, meaning it doesn't utilize the screen effectively. Font size 20 exceeds the screen height, making it invalid. However, font size 15 is the largest size that satisfies both conditions: the sentence fits within the screen width and height at this size. This process requires evaluating each font size in the list to ensure it meets the criteria. Now, consider another example where the sentence is hello, the screen width is 200, the height is 50, and the font sizes are 10, 12, 14, 16. In this case, all the font sizes fit within the screen dimensions, but font size 16 is the largest one that satisfies the conditions. This demonstrates how the goal is not just to find any font size that works, but the maximum possible size. Finally, let's look at an example where no font size is valid. For the sentence fit with a screen width of 10 and height of 10, and font sizes 5, 10, 15, the output is -1. Here, even the smallest font size in the list cannot fit the sentence within the screen dimensions. This scenario highlights the importance of handling edge cases where the function needs to return -1 when no valid font size exists. To solve this problem efficiently, you must consider the constraints carefully. The length of the sentence can go up to 10 to the power of 4, and the size of the fonts array can be as large as 10 to the power of 5. Additionally, the font info methods can only be called up to 5*10 to the power of 5 times, so it's critical to minimize unnecessary API calls. A binary search approach is recommended to efficiently narrow down the maximum font size that works, as it reduces the number of checks required. Edge cases, such as a single character sentence, large screens, or unsorted font arrays, must also be handled appropriately to ensure the solution is robust and meets the problem's requirements. When solving the problem of finding the maximum font size to fit a sentence within a screen, we can start by considering a few different approaches. The first is the brute force method. The idea here is simple: start with the smallest font size and incrementally increase the font size one step at a time. For each size, we calculate the dimensions of the rendered sentence and check whether it fits within the screen's width and height. This approach is straightforward to implement, but it comes with a significant drawback. Since we need to calculate the dimensions for every possible font size up to the maximum, the time complexity becomes O(m*n), where m is the maximum font size and n is the number of characters in the sentence. This inefficiency makes it impractical for large font ranges, particularly when m is very large, such as 10,000 or more. A more efficient alternative is the binary search approach. Instead of iterating through every font size, binary search leverages the fact that for any given font size, the sentence either fits or it doesn't. This creates a monotonic relationship. By repeatedly dividing the search range in half, we can quickly narrow down the maximum font size that works. In the binary search approach, we start by defining the range of possible font sizes, from the minimum to the maximum allowable size. At each step, we calculate the midpoint of the range, referred to as midfont, and compute the dimensions of the sentence at that font size. If the sentence fits within the screen, this means we can potentially use an even larger font, so we adjust our range to explore the upper half. On the other hand, if the sentence does not fit, we move to the lower half of the range to explore smaller sizes. This process continues until the range of possible sizes converges, leaving us with the maximum font size that allows the sentence to fit. The binary search approach is much more efficient than brute force because it reduces the number of font size checks from O(m) to O log m, and since each check takes O(n) to compute the dimensions, the overall complexity becomes O(n) log m. While the binary search approach is slightly more complex to implement, the trade-off is a significant improvement in performance. Another potential optimization involves pre-computing font dimensions for all possible sizes. By storing these measurements in a lookup table, we can avoid recalculating them during the algorithm. However, this introduces higher memory usage and pre-processing overhead, which may not be ideal in scenarios where font metrics or screen dimensions change frequently. After evaluating these approaches, the binary search method stands out as the optimal solution for this problem. Its efficiency is a key advantage, as it drastically reduces the number of font size checks to O log m, making it scalable even for large font ranges. Additionally, it strikes a good balance between runtime performance and implementation simplicity. While pre-computing font dimensions could further reduce runtime during execution, it comes at the cost of high memory usage and pre-processing time, which makes it less practical in most scenarios. The binary search approach avoids these pitfalls while still delivering excellent performance. The core insight that makes this possible is recognizing the monotonic relationship between font size and whether the sentence fits on the screen. This allows us to eliminate half of the search space in each iteration, ensuring that we reach the optimal solution quickly. In summary, binary search offers the best combination of speed, simplicity, and scalability, making it the most suitable approach to solve this problem effectively. This problem involves finding the maximum font size that allows a given sentence to fit within the dimensions of a fixed width and fixed height screen. Each font size corresponds to specific dimensions for a single character, meaning that both the width and height of the text will depend on the chosen font size. To solve this efficiently, we use a binary search approach. Instead of testing every font size sequentially, binary search allows us to zero in on the solution more effectively by repeatedly dividing the range of possible font sizes in half. The first step in our process is to define the problem constraints. The inputs include the sentence to fit, the screen dimensions, a list of available font sizes, and a function that provides the character dimensions for a given font size. The goal is to find the maximum font size such that the entire sentence fits within the screen's width and height. If no font size satisfies this condition, we need to handle it appropriately by returning an error or special value. The binary search process begins by initializing the boundaries of the search space. We set the lower bound, low, to the smallest available font size and the upper bound, high, to the largest available font size. Within the binary search loop, we calculate the midpoint, mid, as the average of low and high. The function char_dimensions, mid, is then used to determine the width and height of a single character at this font size. Using the character dimensions, we compute the total width required for the sentence by multiplying the number of characters in the sentence by the character width. The total height of the text is simply the character height. If the sentence fits within the screen dimensions, meaning the total width does not exceed the screen width and the total height does not exceed the screen height, the font size mid is valid, and we adjust the lower bound to search for larger font sizes. Otherwise, we adjust the upper bound to search for smaller font sizes. Once the loop ends, the upper bound will hold the largest font size that satisfies the constraints. The binary search approach is particularly well suited for this problem because the function fits, mid, which checks whether the sentence fits the screen for a given font size, is monotonic. This means that if a font size fits, all smaller font sizes will also fit, and if a font size does not fit, all larger sizes will fail as well. This monotonic property makes it possible to use binary search, allowing us to reduce the search space logarithmically. For n available font sizes, the algorithm will perform at most O log n iterations. Additionally, the algorithm gracefully handles edge cases. For example, if all font sizes are too large to fit the screen, the algorithm returns -1 or an appropriate error value. Similarly, if the screen dimensions are too small to accommodate any text, our implementation ensures this is handled without failure. The input parameters, such as the sentence, font sizes, and the function to retrieve character dimensions, are processed efficiently using intermediate variables like low, high, mid, and the calculated dimensions for the text. This structured approach ensures clarity and effectiveness. The time complexity of this algorithm is O log n, where n is the number of available font sizes. This is because the binary search reduces the search space by half in every iteration, and each iteration involves only a constant time computation of the text dimensions. The space complexity is O(1), since the algorithm uses only a small number of variables to track the search bounds in the current state. To further optimize the process, we can pre-compute the character dimensions for all font sizes and store them in a dictionary. This is particularly useful if the char_dimensions function is computationally expensive. Another optimization is to implement an early exit strategy. If a font size is too large to fit the screen width or height, we can skip checking larger sizes altogether. These optimizations help improve the efficiency of the algorithm, especially for larger inputs or complex font dimension calculations. Let's walk through an example to see the algorithm in action. Suppose we have the sentence "Hello World," a screen width of 100, a screen height of 20, and font sizes ranging from 1 to 10. The function char_dimensions, f, returns the width and height per character as f*5 and f*10, respectively. We start by initializing low to 1 and high to 10. In the first iteration, the midpoint is calculated as 5. The character dimensions at font size 5 are 25 for width and 50 for height. The total width required for the sentence is 11 characters multiplied by 25, which equals 275. The total height is 50. Since these dimensions exceed the screen size, we adjust height to 4, eliminating larger font sizes from the search space. In the second iteration, the midpoint is recalculated as 2. At this font size, the character dimensions are 10 for width and 20 for height. The total width for the sentence becomes 11 times 10, which is 110, and the total height is 20. While the height fits, the width still exceeds the screen dimensions, so we update height to 2. Finally, in the third iteration, the midpoint becomes 3. The character dimensions at font size 3 are 15 for width and 30 for height. In this case, the sentence does not fit, and we adjust high again to 2. When the loop ends, the variable high holds the value 2, which is the maximum font size that allows the sentence to fit within the screen dimensions. Thus, the algorithm returns 2 as the result, successfully identifying the largest font size that satisfies the constraints. This solution implements the binary search algorithm to determine the maximum font size that fits the given sentence within the screen dimensions. The maxFont function takes the sentence, text, screen dimensions, width, height, available font sizes, fonts, and a font info object to query font-specific metrics. First, a helper function canFit is defined. This function uses the font info object to check if a given font size allows the text to fit within the screen's width and height constraints. Specifically, it queries the text's width using fontinfo.getWidth and the height using fontinfo.getHeight. If both dimensions fit, the function returns true. Then, a binary search is performed on the list of font sizes. The left and right pointers start at the beginning and end of the fonts list. The mid-index is calculated, and the canFit function is used to check if the font size at fonts, mid, fits within the screen. If it fits, the current font size is a candidate for the result, and the search continues in the larger half, to find a potentially larger valid font. If it doesn't fit, the search narrows to the smaller half. The variable best_font keeps track of the largest font size that fits. If no font size fits, it remains -1. The function returns this value as the result. This approach ensures efficient computation with a time complexity of O log n, where n is the number of font sizes. Here, we begin by importing the necessary utilities and defining the Java implementation for the problem maximum font to fit a sentence in a screen. The solution class includes an interface called fontinfo, which represents the methods provided in the problem description. The two key methods within FontInfo are getWidth, which calculates the width of the text for a given font size, and getHeight, which determines the height. Next, we define the maxFont method, which takes the text, screen dimensions, an array of font sizes, and an instance of FontInfo as inputs. Within this method, we include a helper function, canFit, to check whether a specific font size allows the text to fit within the defined width and height of the screen. This helper method calculates the text's width and height using FontInfo methods and ensures both dimensions are within the constraints. Additionally, to determine the maximum font size efficiently, we initiate variables for binary search, including the left and right pointers and a variable bestFont to store the result. The implementation proceeds with a binary search loop to identify the largest font size that fits the screen dimensions. The while loop runs as long as the left pointer is less than or equal to the right pointer. Inside the loop, we calculate the midpoint and check if the font size at this index satisfies the canFit condition. If the font size fits, we update bestFont to store this value and shift the left pointer to mid+1 to explore larger font sizes. If the font size does not fit, we move the right pointer to mid-1 to focus on smaller fonts. This binary search effectively narrows down the search space, leveraging the sorted order of the fonts array. Finally, once the loop completes, the method returns bestFont, which holds the maximum font size that satisfies the given constraints. To solve this problem, we begin by considering a simple example where the input text is hello, the screen dimensions are 100 units wide and 20 units tall, and the available font sizes are 10, 15, 20, 25, and 30. The FontInfo API provides two key methods, getWidth, which calculates the width of the text using font_size len, text, and getHeight, which simply returns the font size. Initially, we set up variables for binary search, left at the start of the fonts array, right at the end, and best_font initialized to -1. In the first iteration of the binary search, we calculate the middle index as 2, corresponding to font size 20. Using the FontInfo methods, we find that the text width is 100 and the text height is 20. Both dimensions fit within the screen constraints, so we update best_font to 20 and move left to 3, aiming to explore larger font sizes next. In the second iteration of the binary search, we calculate the middle index as 3, corresponding to font size 25. Using the FontInfo methods, we find that the text width is 125 and the text height is 25. Here, the text width exceeds the screen width, so font size 25 does not fit. To explore smaller font sizes, we move right to 2. At this point, left is greater than right, signaling the end of the binary search. The largest font size that fits is stored in best_font, which is 20. Therefore, the output for this example is 20. Now, let's examine a second example where the input text is Hello World, the screen dimensions are 150 units wide and 30 units tall, and the available font sizes remain the same, 10, 15, 20, 25, and 30. Using FontInfo, we calculate the width as font_size len, text, where the length of the text is 11. Initially, we set up left at 0, right at 4, and best_font at -1 to begin the binary search. In the first iteration, the middle index is 2, corresponding to font size 20. The text width calculates to 220, and the text height is 20. Since the width exceeds the screen width, font size 20 does not fit. We adjust right to 1, narrowing the search to smaller fonts. In the second iteration of the binary search, we calculate the middle index as 0, corresponding to font size 10. The text width calculates to 110, and the text height is 10. Both dimensions fit within the screen constraints, so we update best_font to 10 and move left to 1 to explore larger font sizes. In the third iteration, the middle index is 1, corresponding to font size 15. The text width calculates to 165, and the text height is 15. Here, the width exceeds the screen width, so font size 15 does not fit. To explore smaller sizes, we adjust right to 0. With left now greater than right, the binary search ends. The largest font size that fits is stored in best_font, which is 10. Therefore, the output for this example is 10. The output for the second example is 10. Now, let's consider a third example where the input text is a single character, a. The screen dimensions are 5 units wide and 5 units tall, and the available font sizes are 1, 2, and 3. The font info methods calculate the text width and height as equal to the font size. Initially, we set up left at 0, right at 2, and best_font at -1 to begin the binary search. In the first iteration of the binary search, the middle index is 1, corresponding to font size 2. The text width and height both calculate to 2, which fit within the screen dimensions. We update best_font to 2 and move left to 2 to explore larger font sizes. In the second iteration, the middle index is 2, corresponding to font size 3. The text width and height both calculate to 3, which also fit within the screen dimensions. We update best_font to 3 and move left to 3 to continue searching. At this point, left is greater than right, so the binary search ends. The largest font size that fits is stored in best_font, which is 3. The output for this example is 3. By following this approach, we use binary search to efficiently determine the largest font size that fits the given text within the screen constraints, leveraging the Font Info API for width and height calculations. This method ensures that we find the optimal font size while minimizing computational overhead. To analyze the time complexity of the algorithm, we start with the use of binary search to determine the maximum font size that fits the given text within the screen dimensions. The binary search algorithm works on the sorted array of font sizes, and at each step, it reduces the search space by half. This means the binary search performs O log n iterations, where n is the length of the fonts array. Now, within each iteration, we utilize a helper function called canFit. This function performs two key operations. First, it fetches the text width by calling fontinfo.getWidth, font_size, text. The time complexity for this operation is O, m, where m represents the length of the input text. Second, it fetches the text height by calling fontinfo.getHeight, font_size. Since this operation only depends on the font size, it has a constant time complexity of O1. As a result, the overall time complexity for the canFit function is dominated by the O, m operation for computing the text width. Combining this with the binary search iterations, we can derive the overall time complexity of the algorithm, which we'll discuss next. The overall time complexity of the algorithm is derived by combining the number of binary search iterations with the cost of the canFit function. Since binary search performs O log n iterations, and each iteration involves calling canFit, which operates in O m time, the total time complexity becomes O log n multiplied by O m. This gives us a final time complexity of O m log n. Now, for the space complexity, we analyze both input storage and auxiliary space. The input variables, which include text, width, height, and fonts, do not require any additional space beyond their initial sizes. For auxiliary space, the binary search process only requires a few pointers, such as left, right, mid, and best_font, all of which use constant space, O1. Additionally, the canFit function does not allocate any extra memory apart from its local variables. Therefore, the overall space complexity of the algorithm is O1, as it does not scale with the size of the input. When we compare this approach to a brute force method, we can clearly see the efficiency of the binary search. In a brute force approach, we would iterate through the fonts array sequentially, testing each font size one by one to determine if it can fit within the screen dimensions. For each font size, we would call fontinfo.getWidth and fontinfo.getHeight, resulting in O m operations per font size. Given that there are n font sizes, the total time complexity for the brute force approach is O n*m. On the other hand, binary search reduces this complexity to O m log n by systematically having the search space at every step. This makes the binary search approach significantly faster, particularly for larger values of n. Breaking it down further, we can analyze the best, average, and worst case scenarios. Even in the best case, where the valid font size is found in the early iterations, the algorithm still performs O log n binary search steps, each requiring O m operations. In the average and worst cases, where the search progresses deeper or the valid font size doesn't exist, the complexity remains O m log n, making this method consistently efficient. The mathematical foundation of the algorithm confirms its efficiency. With binary search, the search space is halved at each step, resulting in at most O log n iterations. For each iteration, the canFit function is executed, which involves O(m) operations to compute the text width and height. When we multiply the number of iterations, O log n, by the cost per iteration, O(m), we arrive at the overall time complexity of O(m) * log n. This efficiency makes the algorithm optimal for the problem constraints, as it balances minimizing the search space with the computational cost of validating each font size. By leveraging the properties of binary search and efficiently handling the operations within canFit, the algorithm achieves a significant improvement over brute force approaches, both in terms of practical performance and theoretical complexity. One common mistake when solving this problem is not accounting for edge cases. For example, you might assume that the input sentence will always fit the screen when using the smallest font size. This isn't always true, especially when dealing with extremely long sentences or very small screens. It's important to validate your inputs to avoid unexpected errors. Another frequent error is using a linear search to iterate through all possible font sizes. This approach results in a time complexity of O(max_font), which is far less efficient than the O log max_font achievable with binary search. Finally, some misunderstand the relationship between font size and the area required on the screen. Font size doesn't scale linearly, instead, it scales quadratically because both the height and width of the text increase. This means the area required grows much faster than you might initially anticipate, so your calculations need to account for this nonlinear relationship. Another issue arises when the fit function isn't validated correctly. This function determines whether the sentence can fit within the screen dimensions, but incorrect assumptions about padding, margins, or text wrapping can lead to results that are either too optimistic or unnecessarily restrictive. It's crucial to account for these layout details to ensure accurate results. Additionally, ignoring floating point precision issues can cause subtle but significant errors. For example, when working with screen dimensions and scaling font sizes, small precision errors can accumulate, especially at larger font sizes. These errors can lead to incorrect conclusions about whether a sentence fits or not. Always consider precision when performing calculations involving floating point numbers in this problem. When tackling this problem in an interview, there are some key insights to keep in mind. First, make sure you fully understand the problem's scope. This means clarifying the input constraints, such as the range of font sizes, screen dimensions, and text length. Once that's clear, leverage binary search effectively. Since the problem involves finding the maximum font size that satisfies a condition, binary search is both optimal and expected in your solution. To support this, optimize your fit function, as it will be called multiple times during the binary search. An efficient implementation ensures your solution performs well overall. Interviewers may also ask about trade-offs. For instance, while brute force is simpler to implement, it's far less efficient than binary search. Finally, demonstrating an awareness of real-world applications, like responsive web design, can help you stand out by showing that you understand the practical implications of this problem. This problem shares similarities with a few other LeetCode problems, particularly those that utilize binary search to solve optimization challenges. For example, LeetCode 875, Cocoa Eating Bananas, involves a binary search approach to find the maximum or minimum value that satisfies a given condition. Similarly, LeetCode 1011, Capacity to Ship Packages Within D-Days, requires binary search to determine the minimal capacity needed to meet specific constraints. Another related problem is LeetCode 410, Split Array Largest Sum, which combines binary search with a greedy approach to minimize the largest sum. While LeetCode 792, Number of Matching Subsequences, may seem less directly related, it also involves efficient validation of conditions within constraints. Exploring these problems can help you deepen your understanding of how binary search and iterative checks are applied in various scenarios. When considering alternative approaches to solve this problem, the brute force method is a straightforward option. This involves testing all font sizes from the smallest to the largest and checking if the sentence fits. While simple to implement, it's highly inefficient, with a time complexity of O(max_font fit_function_time). A better approach is to use binary search, which allows you to efficiently narrow down the range of font sizes. This achieves a time complexity of O log max_font fit_function_time, making it much more scalable. However, it requires careful implementation of the fit function. Finally, a mathematical optimization approach involves deriving a formula to calculate the maximum font size directly based on the screen dimensions and text length. This method is extremely fast, with 1 time complexity, but it can struggle with edge cases or complex constraints. Each approach has trade-offs, so it's important to choose the one that best balances simplicity, efficiency, and accuracy for the given problem. Thanks for sticking with us through this walkthrough. To recap, we used binary search to efficiently determine the maximum font size that fits a sentence on a screen. Remember to practice and apply these concepts to similar optimization problems. If you enjoyed this, don't forget to like, subscribe, and join us for more coding challenges. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!